I'm excited for a post-pandemic summer. We're almost there. So, welcome. Our project that we'll be showing is it takes a Wasm file, WAC file specifically, and compiles it down to LVMIR, where from which it is executable on the machine. So, it doesn't really need any other dependencies, but it can also be used as a module if that's how it's being compiled. As a submodule being run from a different C file, which is how we do most of our testing, as well as our little demo that we'll show in a bit. So just wanted to do a little history. Initially, this project started off as a Wasm runtime. We found ourselves quite in the deep end trying to figure out, like, wait, what is Wasm again? And like figuring out, like, how are we parsing it, or like what are we doing, and like how are we like initializing these things. And we were trying to work with Wasm micro runtime, and took like half a day to compile on my little humble single core machine. Like it was difficult. Um, so we pivoted to something that's like closer to Wasm itself. We just like took Wasm and we wanted to like get it running on the machine. So from Wasm to machine code, and we chose MIPS as our sort of assembly language because two of our members were TAs for a MIPS course. But as we kind of found out, you can't really run MIPS anywhere. And so, and of course, like, we were like having to allocate registers and like pop things on and off the stack with like 5 different lines or something. And so we pivoted once again and finally to what we have now, which is a Wasm to LLVM compiler written in Haskell. The rationale between using Haskell, which we did start off from the beginning, it's a fun functional language. You can't spell functional without fun. And we didn't, the majority of the group didn't know it. So Mac, he, led us through quite a bit of the Haskell monadic stuff, fixing a lot of what we were writing badly into good code, and just being there. So shout outs. And then LVM, of course, much easier to write than writing plain ASM. We get a lot of optimizations free, and we don't have to manage registers. And also we can like create functions and things. I don't know. It's much easier. And I think this brings us to our project demo. And our project demo, we have Conway's Game of Life is what we'll be showing off. So we have here in a Wasm file Conway's Game of Life written, which uses memory for the location of all of its cells, tables just to kind of show off tables. Like it doesn't really, it's using tables for fun. And of course, this could be executable within the, like if we were to just compile it down, but we also export a underscore main function to be able to compile or like to initialize it within a C, within a different C main function to be able to use it as a submodule. And it's classic evolving all cells. It has a little increment, a little thing that checks whether cells are alive or dead. And it is, so we take this like Wasm file and we have changes. Sure. So we take this file from Wasm and we convert it, or we compile it to LLVM, from which we compile it to LLVM, and from which we then take it into an object file type, and we link that with our runner, our little runner. All it does is it just takes some arguments for how many cells we want to initialize, sets the initial cells randomly, and then it starts ticking away, and it just kind of calls tick, and it calls get cell to kind of like render those for us visually. And I compiled this down earlier to a couple different ones just because it's like randomness is fun, but sometimes little guidance helps. So like this just kind of sets the first, I think 500 cells is what I gave it. Alive starts making these like cute patterns vis-a-vis Game of Life, and of course we can go about it randomly. So yeah, random. It just like always ends up with these like scattered life forms. Um, Not very fun patterns. And that's our demo. I'll just, I'll let it run. I'll let it run. Cool. But yeah, using memory, using tables, um, and kind of working.
Here is our code structure for the project. So under the root folder, there's these three major components: main, source, and wasm test. The main folder contains a single file called main.hs, which it takes in the input file from data path we specify in the command. Then it calls some magic function compile, and it will write the result to the output LL file. In the source folder, we're trying to break down what parser gives us and compile the module. lib.hs is our main file and handles the general AAST generation related to modules, functions, memory types, global tables, based on different parts of the parser, which we will take a little bit more look into in the next slides. External.hs is the one where we get all the LLVM functions and other external functions that may be necessary in generating the result. One of the examples of the LLVM function can be the cell function, the math.cell and math.floor function that defined in the LLVM. Gen.hs is where we deal with scope and block from Wasm and define some monads to help the AST generation. Util.hs is just some helper function that are used across lib.hs. And Wasm test, Kunal in the next few slides is gonna talk a little bit more on the test we given. So how did we deal with get the parsing from Wasm to some readable format? This package, language.wasm, helps us a lot. So it does is that it reads in a WAT file and generates a module that contains all of the fields here. So it has types, functions, tables, memories, and everything. So one of the things to note here is that tables here can actually have only one component because WASM module has a single table, has only a single table. And for the AST generation, we use the LLVM.ast package, and each WASM module will be converted to corresponding LLVM module. The code gen is LLVM pretty, and what it does is it takes in a LLVM.ast module and put that into pretty LLVM text.
We began testing by checking if the compiler was able to correctly generate a program in the LLVM IR by just checking the LL file and seeing if the generated code was the skeleton code was correct. Then we set up an environment to test our actual code and the individual instructions themselves. We tested our compiler using a C program which was linked to the functions in the LLVM code generated by our compiler. We started testing each WASM instruction individually by writing out instructions in WASM functions, passing values to those functions through our C tester program, and then the C tester program checked what those functions returned to ensure that each instruction was behaving the way it should be. Um, Control flow testing was similar to the testing of individual instructions, where we tested the functionality for the different constructs simply by um, writing separate functions that implemented those constructs and then checking that they behaved correctly. This was simple since constructs like if else and loops are meant to behave in a specific form, like in a specific way. We also did some random testing where we wrote a few random programs to see if any of them would cause the compiler to break or to see if we missed out on the functionality of any particular instruction on specific inputs. Um, for example, you can take John Conway's Game of Life, something that we were playing around with, which we decided to use for our demo. This diagram represents how the compiler and testing was structured. The compiler itself had methods that compiled the wasm module, uh, in which called methods for each individual function. The compile function uh, methods in Haskell were in the compiler were the ones that also allocated memory and managed the names of the various variables and functions. Um, inside and the final layer was the compile instruction, which was written for each individual wasm instruction. um, they which could map to either one or more LLVM instructions, some of them requiring blocks of code to get the right functionality. Switching to the idea for our project so late into the term um, meant that we had a bit of a time uh, issue, and some of the challenges we faced to get this done in a few weeks were that some of us weren't familiar with Haskell at all and had to learn Haskell, and part of writing a compiler for something else in Haskell made it that we had to be fairly familiar with the types and the difference in Haskell being a purely functional language in comparison to programming languages like C and Java made that quite challenging. Getting working import functionality was also another difficulty that we faced while trying to work on this project, and linking our compile code to the standard C library for testing also took a bit of time. We had to figure out exactly how to link those files and ensure that we didn't break any of the code that we compiled because of the addition of the standard C library. Linear memory also gave us some trouble. We had to make sure that we didn't um, allocate memory incorrectly. Um, had we more time, some improvements that we could have made to this project were that we could have um, optimized it from a security standpoint. Our compiler isn't exactly the most secure right now just because of how we've handled memory and tables. And we haven't implemented a robust type checking system. Given another couple of weeks, we would have done that. And um, we would have also liked to test our compiler further for efficiency and error handling with random inputs and inputs that are unexpected. Currently, a large part of our testing has been limited to working Wasm programs as compared to Wasm programs that have errors. Um, Thank you for your time.